In this video, we'll cover acid and base kind of concepts and definitions. We'll leave the pH calculations for the next video. So for 19.1, the big thing we need to be able to describe are the properties of an acid and the properties of a base. So for an acid, there are a couple things that acids have in common. They always are hydrogen plus something, and what the something is a non-metal. So acids are always hydrogen plus a non-metal. Acids are also sour if you were to taste them. Most acids we don't want to taste, but most acids also can be fruits. So things like oranges, lemons, those are all citric or acidic things. Acids are generally sour if we were to taste them. They react with metals. Acids also have a pH that's less than 7. And so we'll talk about the pH scale in a second, but acids have a pH that's less than 7. Acids also, they turn litmus paper, so they turn blue litmus paper, and litmus paper is just something that we can use to figure out the pH of things, but it turns blue litmus paper red. Okay? So then if we switch over and look at some properties of bases, bases are generally a metal, so we can pick any metal, and they have hydroxide or OH with them. Okay? Bases are generally slippery or bitter. So slippery if we touch them, and bitter if we were to taste them. A lot of bases, though, we don't want to taste. Things like bleach and detergents are considered to be bases. Bases have a pH greater than 7. Okay, so between 7 and 14, those would be bases. And bases turn red litmus paper, and we said litmus paper is just something that we can use to figure out the pH of things. It turns red litmus paper blue. So you can think of acids turn red, the paper red, bases turn the paper blue. Okay. Next, if we go into looking at the pH scale. Okay, so I'm going to erase this and write the pH scale. So the pH scale is a scale that runs from 0 to 14. 7 is right here in the middle. Okay? So this is the pH scale. The pH scale, it measures the amount of hydrogens. So it measures amount of hydrogens. And I'm going to write hydrogens as H+. So we're keeping track of the amount of hydrogens that are just floating in the solution. If the pH value that they give you is a number between 0 and 7, these are where the acids kind of hang out. Anything from 0 to 7. We can have negative pH values. That just means it's a very, very, very strong acid. Okay? And then anything between 7 and 14 is a base. Okay? So if we kind of define this even more, things that have pHs closer to 0, these are where your strong acids live. So strong acids would be things like a pH of 0, pH of 1 or 2. pH is closer to 7 on this side. These are where your weak acids are. So pHs of, let's say, 6 or 6.5. They're going to be weak acids, like vinegar is an example of a weak acid. Things closer to 7 on the other side where we're bases, so things like 7.5 or even 8, those are considered weak bases. Like soap. Things closer to 14, these are where we have our strong bases. And so an example of a strong base would be like bleach is a strong base. So the closer we are to the ends, whether it's 0 or 14, those are where the strong things live. So closer to 0 are your strong acids, closer to 14 are your strong bases. Your weak acids and bases are going to be on either side of 7. Right? If we're exactly at 7, that's where we are neutral. So we're neither an acid nor a base. Things at 7 would be like blood is considered about neutral. Water is also an example of something that's neutral as well. Okay. One other thing to note with this pH scale, we said pH measures the amount of hydrogen that you have. Acids have high amounts of hydrogen. So they have a lot of hydrogen for acids. So the more hydrogens you have, the lower the pH. So I'll write that here. So the more hydrogens, or higher the amount of hydrogens, the lower your pH. So the more hydrogens, we can also think of this as being the more acidic you become. So things that have a pH of 0 or 1, they have lots of hydrogens. So that makes them very acidic. That makes them have a very low pH. Bases don't have as many hydrogens as the acids do. So generally speaking, the fewer the amount of hydrogens you have, the higher your pH. So you would think the more hydrogens, the higher the pH. It actually goes in the opposite direction. The more hydrogens you have, the lower your pH, the more acidic you are. For bases, they have fewer hydrogens in comparison to acids. So the lower the amount of hydrogens, the higher your pH, the more basic you are. So one thing to really keep in mind for this pH scale is we're measuring the amount of hydrogens. Okay? So depending on the amount of hydrogens you have, you may either fall at being an acid or maybe fall at being a base. Okay? Things that are neutral. So the reason why they would be neutral, and you guys will learn a little more about OHs in 19.2, things that are neutral like water, the amount of hydrogens they have equal the amount of hydroxides that they have. Hydrogens are considered to be like an acidic character. Usually acids have lots of hydrogens. Usually bases have lots of OHs. So things that are neutral have equal amounts of both of them, which is why they're not really an acid or a base. All right, next, let's go into some of the definitions of what an acid is and what a base is. So what is this? So you guys may have talked about Arrhenius and Bronsted-Lowry and Lewis. These are some scientists that came up with definitions of how we could define what an acid is and what a base is. So we'll go through all of those and kind of see what those definitions really are talking about. So the first one I'll start with is Arrhenius. So Arrhenius was a Swedish scientist in the mid 1800s, and he was one of the first to actually come up with the definition of what an acid is and what a base is. So according to Arrhenius, an acid is anything when dissolved, so a substance when dissolved that produces H plus for hydrogen. Now, not to be confusing for this chapter, you guys will use the word protons to describe hydrogens. We don't mean like protons with like protons, electrons, neutrons. When you guys did that whole atomic structure unit, we don't mean that type of proton. But proton can also mean hydrogens. So Arrhenius would say anything that dissolves and produces more hydrogens. So an example would be if we take something like HCl and we dissolve it and it breaks apart into hydrogen and chlorine, Arrhenius says because this made hydrogen as a product, this would be a base. This would be an acid. Acids produce hydrogen, which kind of makes sense because all acids have a hydrogen in them. According to Arrhenius, a base would be anything when dissolved produces hydroxides. And hydroxides are OH minus. Okay. So if we write an example, let's say we have LiOH. When that dissolves, it's going to break apart into lithium and hydroxide. So according to Arrhenius, because this makes hydroxide when we dissolve it, it would be considered a base. This is generally true. It's not always true. Most bases, not all, but most bases do have hydroxides. So when we dissolve them, it makes sense that they're able to produce hydroxides that are kind of floating around in the solution. One example of a base that does not have hydroxide, and they will definitely ask this on quizzes and tests, is NH3. This is ammonia. Ammonia is an example of a base that actually does not have hydroxide. So according to Arrhenius, he wouldn't really know how to classify this because when we dissolve, and this actually doesn't dissolve in water, which is one of the issues, it also does not produce hydroxides. So according to Arrhenius, he wouldn't make this a base, but it also does not produce hydrogen. So he wouldn't make this an acid either. So this would kind of be an undefined compound. He wouldn't be able to say whether it's an acid or a base. So this is part of the reason why Arrhenius' definition is a little bit narrow or flawed. It doesn't cover all possible compounds. But Arrhenius was one of the first to propose a definition for what an acid is and what a base is. Okay? The next one that we will talk about is Bronsted and Lowry. Bronsted and Lowry's definition of what an acid and what a base are the definition that we assume to be true, and that's the one that we usually use when we define what an acid is and what a base is. So this is Bronsted, Lowry. So these were two different scientists that came up with this equation and working together, with this definition. So a Bronsted-Lowry acid is a hydrogen. Now remember we said for this unit they may call hydrogens protons, but it's a hydrogen or H plus donor. Okay. So it donates hydrogen, which makes sense because all acids have hydrogens in them. According to Bronsted-Lowry, a base is a hydrogen. Again, we can use the word proton, but it's a hydrogen or proton acceptor. So it accepts the hydrogen. Okay? Now, one thing to note with this definition, the base, according to Bronsted-Lowry, doesn't really use hydroxides to define that it's a base. So this definition is going to allow us to include a lot of other things that Lorania's definition may not have allowed us to include. So let's talk about what this means, hydrogen donor, hydrogen acceptor. Okay, so let's take an example. Let's look at ammonia. Because remember we said ammonia was one of the ones that doesn't have hydroxides, but it actually does behave as a base, and we'll see why that is according to Bronsted and Lowry. Let's say we mix that with water, and let's say this is what we produce. Okay. So when we're dealing with Bronsted and Lowry's definition, we have to track or keep track of how things change. So the ammonia on this side was NH3, but it turned into this guy, NH4, with a plus. Okay? And then let's look at water. We had water was H2O, right? But water turned into OH minus. So we have to keep track of kind of what happened with each of these things. Okay? So if we look at ammonia, we had 1 nitrogen and 3 hydrogens. But over here, we still have 1 nitrogen, but now we have 4 hydrogens. So ammonia added a hydrogen. It accepted a hydrogen to produce, this is ammonium. Okay. So it accepted a hydrogen to turn into that. This one, we had 2 hydrogens and 1 oxygen. Well, that turns into 1 oxygen, 1 hydrogen, so 1 of each. This one actually donated or lost, I'll use the word lost. This one lost a hydrogen to turn into OH minus. Okay, so if we look at Bronsted and Lowry's definition, if we are donating, we are an acid. If we are accepting a hydrogen, then you're a base. So ammonia accepted a hydrogen to turn into this. So ammonia must be the base. It accepted a hydrogen. Okay? If we look at water, water went from having 2 hydrogens and 1 oxygen to 1 of each. It lost a hydrogen or donated it. This would be considered the acid. Okay? So acids donate or give up hydrogens, bases accept hydrogen. So let's look at another example to see if we can figure out who's the acid and who's the base. So let's say that we have HCl plus H2O goes to, and for these types of questions, they would give you the full equation and you're responsible for kind of tracking and figuring out who gave up and who received. So you would be given the full equation and then asked to figure out the acids and the bases. So if we look at this, we want to kind of identify what each thing turned into. This HCl turned into this, just the Cl. This H2O or water turned into this. So we want to look at them so that we can compare what did it have to do to go from this to this? Did it have to gain a hydrogen or lose a hydrogen? So when we look at this, we see that The HCl gave up a hydrogen to turn into just Cl, so it lost a hydrogen. So it lost an H plus. The water went from having 2 hydrogens and an oxygen to having 3 hydrogens and an oxygen. So it actually ended up gaining a hydrogen to get over here. Okay, so if something loses, that means this was the hydrogen donor. This was the donor, it lost the hydrogen. If something gains, this was the acceptor, it accepted it. Okay? According to Bronsted and Lowry, acids donate, so this guy HCl would be the acid. According to Bronsted and Lowry, bases accept hydrogens, so this guy would have been the base. Okay? So this is the acid, this is the base. One important thing also with Bronsted and Lowry is they actually give names to these guys over here. These guys also have names. So the acid turns into, this would be called the conjugate base. We'll talk about what that means in a second. The base, which is the water, it accepted it. This base turns into this guy, we call this the conjugate acid. I know this may seem completely confusing, but they actually switch off. If it was the acid on this side, it turns into the base on this side. If it was the base on this side, it turns into the acid on this side. Now, why would that be true? Now, technically, the reason why that is true is if we were to reverse this reaction and go this way, we'd have to look at what would have to happen on this side for us to go back to here. Well, if we want to go from Cl minus to one that actually has an H with it, this guy would have to accept a hydrogen. If we want to go from here back to here, okay, because if we want to go from where it didn't have a hydrogen to where now it has a hydrogen, this would have to accept a hydrogen. If we want to go from having 3 hydrogens and 1 oxygen to just having 2 hydrogens, this one would have to donate a hydrogen. Okay. So if we're going in this direction, where these are the reactants and these are the products, this would have to lose a hydrogen and this would have to gain a hydrogen. Well, if we look back at our definitions, if you're donating a hydrogen, you're acting as the acid. If you're accepting a hydrogen, you're acting as the base. Now, the reason why we call these conjugates is so that someone knows when you say a conjugate acid or conjugate base, they know that that's on like the right side of your equation. These would be considered the acid and the base, but the acid turns into the conjugate base, and the base on the left side turns into the conjugate acid on the right side. But these would be important things to know because they may have you identify them. So let's actually go back and look at our previous example that we did with ammonia and ammonium and try to identify who is the conjugate acid and who's the conjugate base. Okay, so I'll rewrite that equation here. So we had NH3 plus H2O going to NH4 plus OH minus. Okay, so we said that the NH3 turns into NH4, it gained a hydrogen. So if it's gaining a hydrogen, this was the base, because it accepted a hydrogen to turn into that. This guy was water. Water is going from having 2 hydrogens to just 1 oxygen and 1 hydrogen. This one donated a hydrogen, so this acted as the acid. Okay, and so if we match them up, this NH3 turns into NH4. Well, if it was the base on this side, this would be considered the conjugate acid. Remember they switch. If it's the base on the left, it actually turns into the acid on the right. If water was the acid here, it turns into the conjugate base. One way to also keep track of these is things that have plus charges are your conjugate acids. Plus means they have an extra hydrogen, so they'd want to lose that hydrogen. Things with a negative charge are going to be your conjugate bases. They're already missing a hydrogen, they want to replace it, so they are going to want to gain a hydrogen. Okay, so that's another way we could kind of memorize it if it's easier for you to think of it that way. Now, the reason why we said these are conjugate acids and conjugate bases is that if we were to switch this reaction and now go this way, in order to go from NH4 plus to just NH3, this would have to lose a hydrogen. That's what acids do, they lose hydrogens, according to Bronsted and Lowry. If we want to go from OH minus to back to H2O, where this has 2 hydrogens, This would obviously have to gain another hydrogen so that it would have two. If you're gaining hydrogens or accepting them, you're a base, according to Bronsted and Lowry. So that's why these are the conjugate acid, conjugate base, because if we were to switch those this way, this would lose a hydrogen and this would gain the hydrogen. So hopefully that's a little more straightforward when we get to those definitions. They would definitely, on a question, ask you, they would let you know whether you're doing Arrhenius' definition or whether you're using Bronsted and Lowry's definition to figure out what an acid is and what a base is. But Bronsted and Lowry's definition of an acid and a base as being a hydrogen donor and a hydrogen acceptor is the definition that we usually go with chemistry, kind of the go-to definition. There also is a third definition of acid and bases, and that deals with Lewis, the same guy that did the Lewis dot diagrams. This definition of acids and bases is very rarely used because Lewis's definition deals with electrons. So Lewis's definition of an acid, now this is the same guy we said that did the Lewis dot diagram, so lots of his theories are based off of how electrons are transferred. A Lewis acid is going to be something that accepts, so it accepts electrons. So these guys don't have to do with hydrogens. Lewis's definition is all about electrons. And Lewis says a base is anything that donates electrons. So don't get this confused with Bronsted and Lowry. Bronsted and Lowry say an acid donates a hydrogen, which is the opposite of this. And Bronsted and Lowry say that a base accepts a hydrogen, which is opposite from donating. But Lewis deals with just electrons. So if we look at an example, let's say we have something like this. Let's say we have hydrogen, and we want to add that to this guy, ammonia. So this is ammonia. Okay. And we want to make this. We want to make ammonium. Okay. So the way that this would work is we see these extra electrons here on the ammonia. What would actually happen is the hydrogen would just go and attach to those electrons. So the ammonia would be donating or giving its electrons to hydrogen to make this new bond. Okay, so this has the electrons, it's going to be donating them. So this will donate the electrons, and the E minus. This guy will accept the electrons. Okay? So according to Lewis, if you are accepting, you're an acid. If you're donating, you're a base, which we said is opposite from Bronsted and Lowry. So according to Lewis, this one is accepting electrons, so this would act as the acid. This one is donating the electrons, so this would act as the base. So generally, if they were to ever ask a question about Lewis, they usually don't. If they do ask questions about Lewis, they usually ask you, what is the Lewis's definition for an acid? And you would just have to say that it accepts electrons. Very rarely would they give you an equation like this and ask you to identify the acids and the bases on a quiz or test, just because Lewis's definition is not as widely used for acids and bases because it deals with electrons and not hydrogens, and acids are all about hydrogens. But the acid here would be hydrogen because it's accepting the electrons to make this bond here. And ammonia would be the base because it's donating its extra pair of electrons to hydrogen. All right, so that is actually all of 19.1. One thing I will actually do now before we end the video is briefly review how to name acids and bases, just in case that's thrown in on a quiz. It definitely is something that you guys covered earlier in the year. So if we talk about how to name acids, acids always are hydrogen plus some nonmetal. Now we have a little bit of variety. We can do hydrogen with one nonmetal, or we can do hydrogen with a group of nonmetals. Now your group of nonmetals are your polyatomic ions, like your sulfates, your phosphates, nitrates, those guys. They're just groups of nonmetals. but we have a little bit of variety of how we can make acids. Okay, depending on what kind of category we have or what type of acid we have, will dictate how we name it. So if we were to do this guy, so let's say as an example, we just have HI. Okay, that's just a hydrogen with one nonmetal, whereas here we could have something like, let's say HNO3, hydrogen with a group of nonmetals. If we just have hydrogen with one nonmetal, we use the prefix hydro. This are going to be I call this the nonmetal prefix. We just need the first couple letters of that nonmetal. We don't need the whole name. Okay, and it always ends in ic and then acid. Okay, so this would be hydro. I is iodine, but we don't need the whole name. We just need the first couple letters. So this would be hydroiodic acid. Or if we had HBr, it'd be hydrobromic. Or HF would be hydrofluoric. Let's try this one. Let's say we had H2S. So again, it's still hydrogen with one nonmetal element. We're going to have the word hydro. So this would be hydro to start with. S is sulfur. And sulfur is one of the weird ones. Weird ones. We actually take the whole name. So it'd be hydrosulfuric acid. Okay. So that's how we would name it if it's a hydrogen with just one nonmetal element. If we have hydrogen with a group, okay, it's going to be really important to go back and review your polyatomic names because you may not get them on a test or quiz. So go back and review to make sure you know what carbonate, phosphate, sulfate, all of those guys are. So for the groups, with this hydrogen with a group of nonmetals, we have to know the group name. If the group name ends in 8, like your nitrates, your phosphates, your carbonates, we're going to take off 8 and we're going to put it and then acid. If the group name ends in ites, like your nitrites, phosphites, sulfites, we're going to take off the ITE and put OUS and then acid. Okay? Now it's also very important to keep in mind that these don't have the name hydro with them. Only these. As soon as you see hydro, you should know that it's one hydrogen and one nonmetal. So the way that we would name this guy, since this is nitrate, okay, we're just going to take off the ATE and put ic. Okay? So this went from being nitrate, I'll write it again here. This was nitrate. We took this part off and put ic. Okay? So this would just be nitric acid. Okay, again, no hydro. Let's say, as another example, let's say we had H2SO3. So again, we have to know this group name. That group is called sulfite. So this is sulfite, ITE. We're going to take off the ITE, so we're going to cross that part off, and we're going to put OUS. Okay? Now remember, sulfur is one of those weird ones. We actually wouldn't call this sulfus acid. Sulfur has to take the whole name. So we would actually call this sulfurous acid. Just because the F and the O have that weird sound, we just use sulfurous acid. But the idea is this was ite, so this goes to OUS and then acid. So this is just reviewing how to name acids and bases. If we briefly review how to name bases, bases are really easy to name. Okay. Bases are always a metal, and we can pick any metal with the OH. So any metal with OH. So we can have LiOH, we can have MgOH2, we can have FeOH, we can have KOH. It's any metal with OH. It always has an OH in it, except for the only exception that does not have OH is NH3. You definitely need to know this. Ammonia is a base that actually does not have the hydroxide or the OH part. But the way we name bases is very simple. We just take the full metal name, the first part, take the full metal name, and then they always end in hydroxide. Except for, like we said, ammonia is an example of one that actually does not have hydroxide. So you can just memorize that this is called ammonia. So we would call this lithium hydroxide, iron hydroxide, magnesium hydroxide, potassium hydroxide. So whatever the metal is, we just take that full name, and hydroxide is always going to be the ending of the base's name. So hopefully this was helpful to review 19.1. The next video will cover 19.2, which is all the calculations related to pH.